Good morning. Today I'm going to start talking about absorption kinetics. Absorption kinetics means material that are introduced into the body other than through the IV route would fall under that category of pharmacokinetics. So that would include oral absorption, perhaps even intramuscular or subcutaneous absorption, etc. These are the learning objectives associated with this lecture. So, starting with an understanding about what happens during absorption, unlike in the case of intravenous um, administration, the drug after it's being administered will reach GIT or GI tract um, from where it has to undergo absorption. This step is a critical step that was not present in the previous models, in any of the previous models that we have talked about so far, absorption. After the drug has been absorbed, it can be bound to plasma protein, and depending on the affinity of the drug to the protein carriers, uh, the degree of binding can be different for different drugs. Some drugs are highly protein bound, whereas others are not. Even those drugs that are protein bound will have a certain fraction of the drug that remains unbound. And this fraction that is unbound is a dynamic situation where the bound drug can be released from the protein, or the free drug can be bound to the protein, making it bound. So this can happen within the systemic compartment. From here, um, from the systemic compartment, from the systemic circulation, the drug can actually undergo distribution, where again, during or after distribution, the drug can be bound to receptor sites in tissues. Drug can remain unbound in the tissues. It can be taken to organs of elimination, metabolism, excretion, etc. As far as oral absorption is concerned, um, initially a solid dosage form, as is shown in the schematic diagram, say a tablet, um, after it's been administered or after it's been taken, say with with glass water, will have to undergo a series of steps before it can eventually reach the blood vessels, as is shown in that diagram. So the tablet first will have to undergo disintegration to break down into smaller pieces, and these small fragments will then continually disintegrate, dissolve, and from the dissolved solution, the drug actually forms solution in the GI contents, or the water that was taken along with the tablet. The drug molecule has to diffuse through the membranes, cellular membranes, eventually to reach the systemic circulation, as is shown in that diagram. So, when understanding how formulations perform, there's a science referred to as biopharmaceutics, which is basically the science that tries to understand relationship between the nature and intensity of a drug's effects and the effect of various drug formulations or administration factors. So if the same drug is available as an injection and a tablet, then how the formulation affects uh, the therapeutic effect. Um, the pharmacokinetics, as well as other factors that come in play. That the understanding those factors, that's what is referred to as biopharmaceutics. Now, as far as drug absorption through the oral route is concerned, uh, some of the factors that can impact the drug's effect um, can be broadly categorized into two separate topics. One dealing with the nature of the drug, and the other dealing with the environment from where the drug is being absorbed. So, as far as nature of the drug, two very important points to remember include solubility and pKa of the drug. And this is because the drug that is administered as an oral formulation will have to first dissolve in a medium, and that solubility or that dissolving, the solubilization of the drug in a liquid medium is going to be dependent on its pKa, or the degree of ionization of the molecule. As far as physiological factors are concerned, the pH of the environment, and this is because when drugs are administered via the oral route, um, as it progresses through the GI tract, the drug will encounter a series of environments where there is slight changes and sometimes even drastic changes in pH, as in the case of drug transiting from the stomach into the small intestine. There will be changes in pH, and this may impact the fraction absorbed from a particular environment. Additionally, GI motility plays a very important role with certain drugs. Not all drugs are impacted by this, but some drugs tend to be impacted more than others when it comes to GI motility. This diagram shows a very important, rather demonstrates a very important aspect of GI absorption. The diagram actually shows on the top right corner around here the stomach, and then the stomach leads into the intestine, small intestine, part of which is shown there to show the blood vessels. Some of that small intestine area has been taken out of that diagram. And the small intestine leads to the colon around here, and again the transverse colon, part of that transverse colon is missing there, again to show the blood vessels in the diagram, and the colon leads to rectum. On the top left, you see a very important organ in the GI tract in the body, the liver, and you can see that except for the lower and middle part of the rectum right here, inferior rectal veins and middle rectal veins supply that area. However, the upper rectal region, you can see around here, is supplied by a different veins. So this is one of the reasons why suppositories work. We'll get back to that point later. But note that almost all other parts of the stomach and other organs associated with the GI tract, as well as small intestine, large intestine, all the blood vessels eventually collect together around here. As you could tell, everything else comes together there and eventually goes where? To the liver. This is a transit that cannot be bypassed by any drug that is given through the oral route. Everything and anything that gets through the cell membranes lining the GI tract that eventually reaches the systemic circulation in the veins will have to eventually pass through the liver. And hence, a very important phenomenon associated with biopharmaceutics and pharmacokinetics, as well as drug performance, that we all know, referred to as the first pass effect, hepatic first pass effect, happens um, during this process. Now, I mentioned there's one region, the lower and middle rectum, where there's a different uh, set of veins that carry blood out of that region. If you notice that, that is the only vein, or those are the only veins that did not drain into this um, hepatic um, system that I mentioned earlier. And that's one of the reasons why suppositories can actually bypass hepatic first pass effect, because anything administered um, in this part can actually directly go into systemic circulation without going into the liver. Um, So everything and anything that goes through the cell membranes and eventually reaching systemic circulation will drain into the liver through the portal vein, as is shown on the diagram. This is a very, very important point to remember because it significantly affects eventually the fraction of the administered dose that reaches systemic circulation. Now, the amount of drug that eventually reaches systemic circulation is quantified by using bioavailability. By the way, that is not a definition for bioavailability, but it tells you what bioavailability represents. It represents the amount of drug that eventually reaches systemic circulation. The factors involved as far as bioavailability concerned: absorption, metabolism in the intestinal wall, hepatic first pass metabolism, all of this can have an impact on bioavailability, and the overall oral bioavailability of a drug can be calculated um, using this equation: F oral is equal to F sub absorption times F sub gut times F subhepatic. So each of those F, in fact, the uppercase F is a symbol that is used to represent bioavailability. So as far as the definition is concerned, bioavailability represents the rate and extent of absorption of drug. And in mathematical terms, it represents the fraction of the administered dose that eventually reaches systemic circulation. The overall bioavailability, as was mentioned earlier, just up here, shows that absorption can have an impact, and so that is what is shown in that first factor. Intestinal wall metabolism, or better known as gut wall metabolism, can have an impact on how much eventually reaches the systemic circulation, and that is accounted for here. And the amount that is lost in the liver due to hepatic metabolism is accounted for here in F hepatic. So the overall oral absorption is a product of these separate unique factors. Now, an interesting thing to note is that there can be different scenarios when it comes to oral absorption from formulations. What is shown on the left is a comparison of the plasma concentration versus time profiles, hypothetical plasma concentration versus time graphs of two drugs that are given orally. One undergoes fast absorption, whereas the other undergoes slow absorption. This can also be the same drug given by two separate oral formulations, one from which the drug happens to be absorbed fast or rapidly, and the other from which the absorption is slower when compared to the other. And so, as is usual, the x-axis shows the time, and the y-axis is the concentration. And so, in the case of oral formulations, you would expect to see a gradual rise to a peak, as is shown in this graph, and then a gradual decline. So If you were to compare this graph to this graph, you can clearly see that graph marked 1 shows that the drug appears starts to appear in the systemic circulation much faster, as is shown by the slope here, much steeper slope when compared to graph 2. Similarly, the amount, if you were to compare between the peak of 2 with the peak of 1, you'll see that there's more drug that was absorbed within a short period of time. However, one thing to note though is the overall bioavailability is actually the entire area bounded by these graphs. Okay, so in that sense, although formulation 1 appears to produce a peak faster, although there's rapid absorption from this formulation, the AUCs may not be different. They may be the same. In other words, overall bioavailability may be the same from these two formulations. The only thing that is distinct or different between these two formulations is the rate of absorption. Conversely, on the other hand, on the right side of that slide shows where there are two formulations. Again, let's mark these as one solid line and two broken lines. You'd see that the initial slope or the rate of absorption is similar, if not identical, with these two formulations, as is shown by that slope. However, there is a clear difference in terms of AUC bounded by these two graphs. The graph 1 tends to have a greater area, or seems to have a greater area bounded under that graph when compared to graph 2, and that is the difference between these two formulations. There seemed to be no difference in terms of rate of absorption, but rather the extent, how much eventually got into systemic circulation from this formulation is what was impacted. So trying to understand these subtleties, what factors contribute to this difference, what are the consequences of these differences, that is what biopharmaceutics entails. So F is the symbol that is used to express bioavailability. As far as the definition is concerned, F represents the fraction of drug that reaches systemic circulation. It can also be stated differently as it represents the rate and extent of absorption of drug. And for an oral product, bioavailability F can be determined by determining the amount of drug absorbed and that reaches a systemic circulation divided with the total amount of drug absorbed. So after a particular dose has been administered, you can measure plasma levels at various time intervals and then calculate the total amount that is absorbed over the time interval and divide it with the total amount of drug administered to calculate bioavailability. However, it's much more practical to administer the same drug via the oral route and the IV route and get the relative bioavailability calculated that manner, where then the relative bioavailability F is going to be equal to AUC oral divided by AUC IV. So AUC, area under curve, obtained from the plasma concentration versus time graph after the formulation has been administered orally, or a dose of the drug has been administered orally. You can determine that by administering a certain particular dose to a series of human subjects, and then determining plasma concentration at various time points. You can get the AUC oral that way, and then the same dose, an equivalent dose, can be administered to a separate group of human subjects, and then determine plasma concentration at various time points, and generate a graph and obtain the AUC for the IV formulation. And then if you take the ratio, that'll give you the relative bioavailability. Um, the number that you obtain that manner does not indicate, although the definition includes the rate and extent of absorption, it does not in any way convey the rapidity or the rate at which this process is occurring. As was shown earlier, the rate where the graph that compared the rate of absorption between two formulations, 1 and 2, where one drug was absorbed faster from formulation 1 versus the other. The bioavailability, overall bioavailability, was the same for both drugs eventually, because the AUC bounded by these two graphs were the same. And so the number F, the value that you obtain for F, does not in any way indicate the rate. We cannot assume how fast absorption is occurring from, or we cannot deduct how fast the drug is being absorbed from bioavailability. However, one thing that can be clearly assumed is that a low bioavailability number, F, indicates poor or erratic absorption. And when we have a drug candidate that has low bioavailability, it will be severely impacted by disease-related changes, and such drugs will also have a significant impact. It will be significantly impacted by the gastrointestinal transit times and short bowel syndromes, etc. We're going to use the one compartment model in order to understand the mathematics surrounding oral absorption. We're going to assume first order elimination. These two apply to this model as well. So one compartment model as well as first order elimination. Okay, this is not any different. One of the assumptions which does not hold true for all the drugs is that F is equal to 1. So F is equal to 1 means the entire dose that is administered orally gets absorbed. Another assumption is that the rate of absorption is much faster than the rate of elimination. So that means if the drug gets absorbed really quickly and rapidly into the systemic circulation. And another thing is that there is no distribution lag time. In other words, as soon as the drug is absorbed, it instantaneously distributes throughout the body. And as I mentioned earlier, another very important assumption is that the drug after absorption undergoes first order elimination. And this model can be used to understand pharmacokinetics following the oral route as well as intramuscular route. And the plasma concentration versus time graph, since this is first order elimination, will be plotted using can be plotted using the semi-log graph paper with time on x-axis and plasma concentration in y-axis, and the y-axis is the logarithmic scale, so this is a semi-log graph paper. And you will see that there is a gradual increase in the plasma concentration with time, and then once the absorption is complete at the peak, the plasma level declines with time after that time point. So there are three separate regions that we can mark in this graph. Segment A, segment B, and segment C. In A, what is happening are two processes. There are two processes occurring here, namely absorption and elimination. If you were to compare this to the IV bolus two-compartment model, it's kind of similar. There it was distribution and elimination. Here it's absorption and elimination. Then the absorption happens over the period of time as shown here, and eventually most of the absorption is complete at that point B. And the point B, the peak, in this model sometimes may also be written as Cmax, and the time it took to reach Cmax is referred to as Tmax. So at that point, most of the absorption is complete, and then the slope of the graph tilts downwards, which means that now elimination is occurring at a much, much faster rate than absorption, or rather, in many instances, absorption is complete. And so whatever is left in the systemic circulation then gradually declines with time. So if we have just two levels drawn during the elimination part of the curve, as is shown in the diagram, C1 and C2, corresponding time points being T1 and T2, then the slope obtained by taking natural log of C2 minus natural log of C1 over T2 minus T1 will give you K, which is the elimination rate constant in this model. Okay, so that's the elimination rate constant in this model. And T half will be 0.693 divided by K, and the volume of distribution can be calculated by taking the dose and dividing with the product of K times AUC. And the AUC can be determined using the trapezoidal rule that you're aware of. And the factor Tmax that I described earlier, the time it took to reach the Cmax or peak, can be calculated by using this equation, natural log of Ka over K divided by Ka minus K. Ka is the absorption rate constant, which is something unique to the absorption model. And we will talk more about how you can determine Ka. And now this is an ideal situation where you have two time points and two concentrations. Many times what we encounter during studies is that there's one there, there's one there, there's one there. So you have various levels drawn at various time points. Now when we have a situation like that, you know what to do, right? To calculate K from this part, what you will do is take those, 1, 2, 3, 4, 5. So I have 5 concentrations. So you can do the linear regression route. You have to do linear regression too. Let me write it a little more clearly. So do linear regression. So you can do linear regression to obtain the slope of that part of the graph. So Ka is something unique, and we haven't seen that before in any of the models that we talked about so far. Represents the absorption rate constant. It represents a fraction of drug presented at the absorption site that is absorbed per unit time. So elimination rate constant was the fraction of drug eliminated per unit time. Ka is the um, fraction that is absorbed per unit time. A high Ka greater than say 1 per hour, again Ka being a first order rate constant has the units of per hour, as is the case with elimination rate constant. So it has the units of per hour. So very high Ka greater than 1 per hour indicates rapid absorption. Drugs absorbed slowly will have a smaller peak concentration and may have a long duration of action. And typically, as is the case with KEL or elimination rate constant, Ka does not change, and it is a constant. Now, I mentioned earlier the elimination rate constant can be measured from the slope of the terminal portion of the plasma concentration versus time graph, and elimination predominates at this point, as I mentioned earlier, and absorption does not have an appreciable effect on what happens to the slope at this point of the graph. So absorption does not seem to impact this at all. Absorption does not impact the slope here. So how do we calculate the absorption rate constant? This is through a method that we saw earlier in a two-compartment first order elimination IV bolus. We use the method of residuals. Since absorption is complete by the time the plasma level reaches the peak plasma level, also represented by Cmax, the concentration points up to that point, up to Cmax, is what is used, as is shown here. 1, 2, 3. Those three concentrations are the ones that will be used, can be utilized from this example that is shown on the slide. From the linear regression, we will know the equation for that part of the graph, and it's a first order equation, right? So it will be b exponential negative kt, and intercept, because of that in y-intercept, is what is this is, and then this is the slope or elimination rate constant from that side, and t is time. So using that and the time points corresponding to the first three plasma levels, you can plug that here and obtain the extrapolated values. E1, E2, and E3. So E1, E2, and E3 represent extrapolated values. Okay, and now to determine residual, all we have to do is, and these are the extrapolated values are labeled as A prime, B prime, and C prime. The residual are basically A prime minus A, B prime minus B, and C prime minus C. So we can determine the residuals that way, and then do a linear regression again. I'm going to use a different color for that. So those are these points are the residuals marked by the purple color. You can do a linear regression to calculate the slope and the intercept of that line, and the slope of that line is what Ka is. And we will do a sample problem so that you can understand the entire process very clearly at that time. So the overall equation to determine the plasma level at any time point after an oral dose has been administered can be written in this format. It's similar to the two-compartment IV bolus model, but there the two terms were added together. Here one is subtracted from the other. So C is equal to B e raised to negative KT minus A times e raised to negative KAT. That is the equation that represents the change in plasma level when a drug is given through the oral route that undergoes one compartment absorption, first order elimination, and when the entire dose is completely and entirely absorbed after it has been administered. So K represents the elimination rate constant of that equation. Ka represents the absorption rate constant, T is time. B are the intercepts obtained from performing the linear regression. B represents the linear regression, the intercept, so represents the intercept from terminal phase of the plasma concentration versus time graph. A is obtained from doing linear regression of the residuals. Okay. So, however, we know that many times F is not equal to 1, and when we know the bioavailability of a drug, then the plasma level following oral administration of a dose of a particular F or bioavailability can be calculated using the equation that is shown here. F is the bioavailability, X sub 0 is a dose, Ka is the absorption rate constant, V is the volume of distribution of the drug, and everything else has been already been explained. So this is the equation that can be used to calculate when F is not equal to 1 and F is known. Now if the drug were to be given multiple times, if the drug was taken orally or given intramuscularly over a period of time, and each dose is administered at tau interval, tau is dosing interval. Okay, if that's the case, then this complicated equation can be utilized to calculate the plasma steady state level eventually. So everything else in that equation has been described. F is the bioavailability, X sub 0 is the dose, V is the volume of distribution, Ka is the absorption rate constant, K is the elimination rate constant, T is time, tau is the dosing interval. Um, Many times, apart from a drug being given orally via a conventional immediate release dosage form, drugs will be formulated as controlled release products as well. The main goal when designing controlled release products is to help to overcome repeated dosing and to improve adherence and to prevent drastic fluctuations in drug levels. If these fluctuations can impact drug performance, then it is desirable to have the plasma level maintained within a narrow range over the period or duration of therapy, and hence controlled release products can be formulated to achieve this goal. Um, with controlled release products, one thing to remember is that absorption becomes zero order. In other words, the design or the feature of this particular type of dosage form is done in such a manner that a constant amount, so that is one thing that is different. When we first talked about zero order and first order kinetics, and when we saw the equations for these two processes, zero order or first order process, we saw that in a case of zero order, a set amount, no matter what amount was, say, introduced into the system, a set amount will be eliminated. A constant amount will be eliminated. However, in first order elimination, the amount that was eliminated depended on what was remaining. So the same thing applies here. In controlled release products, the absorption is zero order. The design is such that it'll contain features, excipients, that will allow for a certain amount of drug to be released and hence absorbed after it's been given orally. Now, the control release mechanisms can be achieved through multiple ways: through repeat action, through sustained release, through prolonged action, or through specific intestinal release through utilizing various polymers. You can take the formulation through the stomach to eventually only release it in the intestine, and so on. So these are some of the control release mechanisms that are that go into the design. So the fluctuations in plasma levels shown by bolus oral dose is shown here by these typical sawtooth diagram, and the therapeutic window is here. Therapeutic window is there, and control release products actually release the drug that way. So that is the rationale for using control release product. You see with the first dose there was a peak here, and then it went down here, and then went up there after the second dose, came down here right before the third dose, again went up here, and so those fluctuations, as you can see, can produce toxic levels momentarily or for a short time, and can also take the levels to subtherapeutic levels momentarily or for a short period of time during conventional dosing. And hence, if there are certain drugs for which this is not desirable, then we can formulate control release products to address these issues that is related to toxic as well as subtherapeutic levels that can be produced during normal dosing with using conventional immediate release dosage forms. The average steady state concentrations for such products, control release products, can be calculated using the equation that is shown there. C represents the average steady state. This is not the peak steady state. This is the average steady state concentration. X is the dose, F is the bioavailability, tau is the dosing interval, CL represents clearance. That's the end of this part of the absorption kinetics lecture. We will discuss some sample problems in another video, and a third video will go into details of some special considerations related to oral absorption. Thank you.